Hello, class. One of the next tools that we're going to be learning here in AP Biology is that of statistics. What we want to use statistics for is a way to, statistically analyze our data. Whenever we generate data, we might be able to look at it and compare and contrast and say, hey, look, one set of data looks different than another set. But in order to do so confidently, we have to use statistics to statistically analyze that data. If we remember from the scientific method, one of the steps after the scientific method, one of the steps after collecting data is to is to analyze that data. And a very good way of analyzing data, a valid way or legitimate way of analyzing data is through the use of statistics. Statistics is a way that we can use to analyze data sets in order to qualify them as good, valid, and legitimate. So we're going to be talking about a couple statistical tests that we can use in AP Biology, and then we'll take a look at one in particular that we're going to be taking a look at in the upcoming class. First of all, let's take a look at why we might want to use statistics at all. Firstly, we want to be able to confidently conclude that an independent variable, we know what those are now, but that an independent variable causes real change, significant change to a dependent variable. In order for us to confidently say that, and the key word here is confidently, in order for us to confidently say that, we have to use statistics. More importantly, or more generally, we are just ultimately looking at two groups of data, two sets of numbers. And usually we want to average those numbers, but we're looking at two distinct, discrete sets of data to see if those data are the same or if they are different. Really, that's all statistics tells us. Are two sets of data the same or are they different? All right, and if we can make those conclusions, those data usually represent something larger or a trend. We can come to a conclusion, a scientific conclusion, and that's ultimately the goal. We want to generate explanations with confidence. We want to draw conclusions with confidence. Now, the branch of statistics, whether or not you're familiar with it, is a varied branch. What that means is there are many tests, many tools, many instruments that we can decide if groups of data are the same or are different. We're going to take a look at a few of them, but let's talk about a number of them. There are different kinds of tests known as t-tests. One of those is the standard t-test or a paired t-test. In order to generate a regression curve or a line of best fit, we do what's called a regression analysis. There are other kinds of tests that look like t-tests but are for many more variables at the same time, known as ANOVAs. ANOVA stands for Analysis of Variance. There's a one-way ANOVA, there are two-ways ANOVA, and the real aim of our discussion today is to look at this test known as the chi-square test or the chi-square analysis. Chi looks like chai, but it's pronounced chi. It's a Greek letter. It looks almost like an X. And the chi-square, we put an exponent to it. That is the statistic that we are generating today, the chi-square statistic. And that statistic tells us some important information. So we're going to look at the chi-square analysis today. Before we do look at that specific test, however, let's take even a further step back and understand why statistics are useful. What the title of this slide tells us is that much variation in life, I'm going to underline that word variation, much variation in life is due to random chance and the laws of probability. And those are two important ideas that we want to cover. Let's, for example, think about dice roll. Right? Many of us have rolled dice before, and we know that any given dice roll could be any number between 1 and 6 on a typical standard dice. And if we roll the same dice 2 times, there's a very small chance that you're going to get the same number twice. If we roll it 3 times, there's even a smaller chance that we would get the same number 3 times, and so on and so on and so forth. What we see with dice roll is that there is variation in the results, and those variation are predicted by the laws of probability. Each dice roll has 6 sides, and so for every given possibility or every given result, you have a 1 in 6 chance of getting that result. And if you want to get that result twice in a row, it's a 1 in 6 chance squared. So it's a 1 in 36 chance that that would happen. And so on and so forth. If you want to get it 3 times in a row, it's a 1 in 6 chance to the 3rd power. And so you see, as we operate the dice more and more frequently, we have a smaller and smaller chance of getting the same number in consecutive rolls. And these all operate based on the laws of probability. The same thing can be said of cards. If you were to draw a card, there is a very small chance, a 1 in 52 chance, that you'd be able to predict that card. In general, since there are 52 cards, there's a 1 in 52 chance of getting each unique card. That is to say, there is variation in when you draw cards. Right? There are many different cards, there are many different options, and due to random chance or the laws of probability, you will get different results on different tries. The laws of variation or the laws of probability also operate, for example, with sprinters. If we're looking at Usain Bolt, for example, he runs his hardest on any given 50-meter dash. He might get a result, one result, and result A, and then he might be off just a tad on the next result, result B. And those results aren't because he's worse or better. It just usually happens due to random chance. Some random events occur such that his timed results, might be slightly different from one run to the next. So, as statisticians, if we recognize that variation exists, that is to say, different results on the same kind of attempt, for example, a dice roll or a card draw, different results are likely to happen, and they are due to the laws of probability or the laws of random chance. Because this variation exists, we can account for it. We can say that sometimes differences are caused by only variation. Nothing else is causing those differences except random chance. So, when in the world of statistics, we generate this hypothesis known as the null hypothesis. The null hypothesis is a hypothesis that states that any variation that we do observe is only and simply due to random chance and the laws of probability. Nothing else is causing you to roll a 6, then a 3, then a 4, then a 2, then a 6 again. Nothing is causing those results except by random chance. Okay, and so that's what the null hypothesis states. We usually abbreviate the null hypothesis as an H sub 0. All right, that 0 is subscripted. Okay, so that's the null hypothesis. That's what the null hypothesis states. The opposite of the null hypothesis would be the alternative hypothesis, null sub A. The alternative hypothesis would be that instead of random chance causing the variation, something other than random chance causes variation. Okay, which is to say that potentially an independent variable causes variation. Okay, and we know what independent variables are. So in statistics, we operate under the assumption that chance is working alone without anything. With the in the back of our heads, though, we know that there is an alternative hypothesis to the null hypothesis. That alternative hypothesis says that no, chance probably isn't working, but instead something other than random chance is working. In statistics, what we're trying to do is we want to be able to accept or reject the null hypothesis. When we accept the null hypothesis, that means that we conclude that random chance alone is acting and that random chance causes any differences or any variation. But when we reject the null hypothesis, that is what we are concluding is that something other than random chance, probably an independent variable, is causing variation. It's causing something that cannot be explained simply by random chance. All right, so again, however, sometimes variation is caused by something other than random chance. If that's the case, we will be rejecting the null hypothesis. Oop, that should be a 0. Okay, that's definitely not a 0. A 0. There we go. The null hypothesis. So if we look back at those examples that we talked about, for example, a dice roll. If we have to reject our null hypothesis, right, if we say that the null hypothesis is not valid here, that we have to explain differences in dice roll that are not explained by random chance. For example, what if my dice were weighted and that weight provided me the opportunity to roll 6s frequently? Well, that would be something other than random chance causing variation. The weighted dice would be causing variation and not random chance. Or if we're talking about our cards, for example, maybe I have 51 cards, or maybe I have 26 cards, and all 26 cards are red cards. And so certainly something other than random chance is causing me to only draw red cards. All right, that is to say, something else or an independent variable is causing the results that are not predicted by random chance. So, in order for us to confidently make those conclusions or make those decisions, we have to use statistics. This is where statistics comes in. When we want to conclude if random chance is likely acting or if something else is likely the cause of that variation. Okay, that's what we're using statistics for. So this first half of this lecture has been an introduction to why we use statistics. Now we're going to start talking about specific tests that we can use. The chi-square analysis is a statistical test. It is a test that compares observed or experimental data with what we expect to occur. All right, so we're taking our observations and we're comparing our observations to expectations. And we want to be able to conclude, are our observations significantly or statistically different than what we can expect to occur due to random chance alone? Okay. Another way of putting it is we're testing whether any differences from expectations are due to something other than random chance alone. Okay. So if we can accept our null hypothesis, we have to say that random chance alone causes our observations to be different from expectations. It's randomly occurring that our observations are different. But if something other than random chance is occurring, then we have to reject our null hypothesis. Something is causing our observations to be different than our expectations. This is what the chi-square analysis allows us to do. This is the purpose of the chi-square analysis. And what we see here is the equation or the formula that we will use in order to calculate the chi-square statistic. Okay, so the chi-square statistic is equal to the summation. Let me write that down, please. And we'll talk more about summations before. We should be relatively familiar with summations. It's the summation of our observations, O, minus our expectations, and take that and square it, and divide that product by your expectations. So it's your observed value minus your expectations or your expected value squared divided by your expectations. Okay, so let's see this in practice. Let's imagine that I have a deck of cards. It's a normal deck of cards. It's got 52 cards, no jokers. It has hearts, spades, diamonds, and clubs. All of those cards are in the deck. It's a normal deck of cards. If I were to draw a card randomly and then put that card back 100 times, so I'm doing this 100 times, my expectation, because there is an equal number of hearts, spades, diamonds, and clubs, because there is an equal number, my expectation is that I should draw each suit 25 times, or 1/4 of the time. So it equals 25 times. I should get 25 hearts, I should get 25 spades, 25 diamonds, and 25 clubs. Now, if I do this 100 times, it's certainly possible that I might not get 25 hearts and 25 spades, 25 clubs, and 25 diamonds. I might get 26 or 24 or 27 or 23 due to random chance. We know that. We know that that's a possibility. And so what I've done is I've come up with some example data. Let's imagine that instead, these are my expectations, and let's imagine that I've done this. I've drawn a card 100 times and put it back. And these were my observed data. These were my experimental data. So you can see I drew a heart 28 times, a spade 24 times, 29 diamonds, and 19 clubs. Okay. Now what I've done here is I've calculated what we call the chi-square value. What I mean by calculating the chi-square value is I took that equation from the previous slide. I'm going to rewrite it. The equation of chi-square is equal to observed minus expected, and we square that, if I can do that, over expected. I've taken, for example, observed 28 minus 25 squared, so that's 9. 9 divided by 25 is a value of 0.36. The same thing here. Observed 24 minus 25 is -1, squared is 1, positive 1, divided by 25 is 0.04. I've done that for all of the suits. So I've got a chi-square value of 0.36, 0.04, 0.64, and 1.44. And like I said, the chi-square value is a summation. That means I take all of my single chi-square values and I sum them. I add them together. So the summation of my chi-square values is 2.48. Before we go any further, I forgot to talk about our null hypothesis. The null hypothesis means will tell us, or the null hypothesis will predict that there is no difference in the suit frequency. That is to say, any difference that we do see is due solely to chance. The alternative hypothesis, however, says that there is a difference in suit frequency and that something else is causing the difference in suit frequency. Okay, so we've calculated our chi-square value. Okay, our chi-square value. We also have to calculate our degrees of freedom. The degrees of freedom is a tricky concept, and I'm not going to get into it too much right now. But how we calculate it is we take the number of groups that we're dealing with. In this case, we're dealing with 4 groups because we have 4 suits. And we subtract 1. Okay, so it's an n is the number of groups, minus 1 equals 4 minus 1. So our degrees of freedom is 3. That's going to be helpful when we try to draw conclusions about whether this is significant data or not. So just to be clear, I want to go over some definitions here, because I know that sometimes this process of calculating a statistical value and drawing conclusions can be sort of tricky. So just to be clear, the chi-square value is the calculated value using our chi-square formula. Again, that was what we had. I think it was 2.48 or something like that. Okay, that's our chi-square value. All right, and what we're going to call that is our test statistic, or our chi-square value. A critical value, however, is slightly different. The critical value is what we're going to call is the threshold value that we will compare our chi-square value. So we're going to take our chi-square value and we're going to look to see how it compares or how it relates to the critical value. Okay? The critical value, it says, deems whether or not your chi-square value is significant statistically or insignificant. Okay? And it allows us to draw a conclusion about whether or not we can accept or reject our null hypothesis. So we take our chi-square calculated value and we compare it to the critical value. Then we can determine if it's significant or not. There's another value that we'll be using to help make this decision, and that value is known as the p-value. The p-value is also recognized as the probability value. We just shorten it to the p-value. It's a decimal or it's a probability in decimal form that your results are due to random chance alone. Okay, so it is our probability that the results are due to chance. We're looking as statisticians and as scientists for a probability that our results are due to chance that is less than or equal to 0.05. So that is to say, if we have a 0.05 p-value, or rather, let me erase that real quick. Okay, let's imagine our p-value, and I've written it previously. If our p-value is less than or equal to 0.05, which is to say a 5% chance that randomness is causing these differences. If our p-value is less than or equal to 0.05, or we have a 5% chance, then our results are significant. They are significant, and we can reject our null hypothesis. Another way of putting this, from the opposite perspective, if we have a 5% chance, or 5% probability that chance is acting, that means we have a 95% confidence that something other than chance is acting. And if we are 95% confident that something besides chance is causing these results, then we can confidently conclude that something else besides chance. Anything greater than 5%, or that is to say, any confidence less than 95%, is not good enough in the scientific world. Scientists have decided that 95% confidence is good enough to make a confident conclusion. So we haven't made a decision regarding our card data. So let's take a look. We had 3 degrees of freedom, and we are shooting for 0.05 as our p-value. Okay, so we take a look and we go all the way over here. All right, and we take a look down here. Okay, 7.82 is our critical value. Okay, and we said that our chi-square value was equal to 2.48. So we ask ourselves, is our chi-square value greater than our critical value? No, it's not. It's not greater. And so as a result, we cannot be 95% sure. In fact, if we look at our p-values, our p-value finds itself in between, these two values, 2.37 and 3.66, which tells us that our p-value looks somewhere in between 0.5 and 0.3. That means our p-value is nowhere near 0.05. In fact, our probability that this is due to chance is somewhere between 50% and 30%, which is nowhere near the level of confidence that we need to be. So what we have to do is we have to conclude that the results that we had with regards to our card selection is simply that variation from our expectation is simply due to random chance. Just because we drew one of the suits at 28 and the other was at 19, there's nothing causing those differences except for random chance. Therefore, we have to accept our null hypothesis. Again, I can't write either. All right, we accept our null hypothesis, and we conclude that random chance is causing this variation. Let's take a look at another example as well. Now here's a problem, and here's a situation. Let me read it to you. An urban economist wants to determine whether the region of the U.S. a resident lives in is associated with their general level of satisfaction with life. He randomly selects 150 residents 18 years of age or older from 4 geographic regions of the United States: the East, the South, the Midwest, and the West. He asks, are you satisfied or dissatisfied with the way things are going in the United States at this time? And here are the results. This is what we see. First of all, our null hypothesis predicts that the satisfaction rating are all the same between all of the regions. Any differences are due solely to chance. Our alternative hypothesis on the flip side would be satisfaction ratings are not all the same between regions, and something else is causing these differences. Okay, so here we see our results. We see satisfaction. These are the people that are satisfied and dissatisfied, and we generate a total. And we have people from the East, the South, the Midwest, and the West, and the total with regards to satisfaction or dissatisfaction. And we see some variation. We don't see exactly the same responses from region to region, and we have to ask ourselves, is this due to random chance alone, or is something else causing these differences? First, what we have to notice in this kind of problem, and you're going to see this kind of problem, this problem is slightly different from our card problem. In this problem, we have two different categories. We have satisfied and we have dissatisfied. And we have 4 different groups within those categories. Okay, so first of all, that's going to influence our degrees of freedom that we calculate. But it also it creates a slight difficulty when we calculate our chi-square value. When we want to generate our chi-square value, how are we doing this? We don't have expected values. All we have are observed values. Well, there's a way that we can calculate expected values. Ultimately, what we have to do, please first notice that we have 337 people as satisfied and 263 as dissatisfied. In order for us to calculate our expected values, we have to sort of evenly distribute 337 between all of these 4 groups, and we have to evenly distribute 263 between all of these groups. One way we can do that is simply to divide by 4, but that might not always work in all cases. So there is a more generalized way of going out and distributing these totals evenly amongst all of our groups, or rather all of our regions. So let's take a look at that way. In order for us to calculate the expected count or the expected values, when we have multiple categories and multiple groups within those categories, like this problem, what you first need to do is generate the table. All right, that table that you saw in the previous graph. That table has all of the data set out properly and has totals for each row and for each column. And so in order for us to generate our expected count, we have to take the total for the row, which was 337 for that first row, and the total for the column, which was 150 for that first column. And we take it and divide it all by the grand total, which was 600. And so I've done that here. I've actually rearranged some of the numbers accidentally, and we have our calculation for expectations. Okay, and so for all of the first row values, our expected count will be 84.25. If we do the same thing for the second row of dissatisfied, we would find a different expected count. And let's see those the expected values on our next slide. So what you'll see is a table that looks almost exactly like the previous table that we saw, except now in red and in parentheses, all of those numbers represent the expected frequencies or the expected counts. So for example, in the East, though we observed 77 to say they are satisfied with the way things are going, our expectation based on our calculation says that we should expect 84.25 people to indicate that they are satisfied. That is true. Our expectations are true in each of the regions because we should expect that there is really no difference between those regions, and any difference might be due to chance. The same thing can be said with our dissatisfaction. We expect that 65.75 are dissatisfied, and that difference is distributed throughout each of the 4 regions. But our observed values, though they may be different, should only be different due to chance alone. And so now, with we have observed data and we have expected data, we can now calculate our chi-square statistic. And so on this slide, what we see is all of the work that you could be doing for our chi-squared statistic. Okay, what we see here is this is our formula for chi-square. And now we would take the first box and we say 77 minus 84.25 squared over 84.25 plus the next box 84 minus 84.25 squared over 84.25, and in the next box, and so on and so forth. And we have all 8 boxes, and we add all of those chi-square values up to generate our total chi-square value. And that total chi-square value will be 3.5405. All right. So now we have a total chi-square value. We have to calculate our degrees of freedom. And remember that I said that this one was a sort of a weird example for our degrees of freedom. We have 2 groups. Okay, so our n is equal to 2. But within each group, our n is equal to 4. Okay, and so we have 2 minus 1 and 4 minus 1, and we multiply those together. And we get our degrees of freedom. 2 minus 1 is 1. 4 minus 1 is 3. 3 times 1 is 3. So our degrees of freedom here is 3. If we look at our chi-square distribution table, or our critical value distribution table, we see that with 3 degrees of freedom, we have a chi-square value, a critical value of 7.815. And we look at our chi-square value, and we compare our chi-square value to our critical value. Since our chi-square value is less than our critical value, that means that our p-value is greater than 0.05. All right, our p-value is not small enough. That is to say, we are not confident enough. Therefore, we are going to have to accept our null hypothesis. Okay, or therefore we do not reject the null hypothesis. There is no evidence to suggest that the distributions of satisfaction ratings differ significantly from region to region. What we can conclude is that the regions are generally equally happy. Though there is variation, that variation can be explained by random chance. So, to sum up, what we've done so far is we've talked about statistics in general, why we use statistics. We've named a few tests, and we've looked specifically at the chi-square test. We've looked at what the chi-square test allows us to do, and we've looked at a couple problems and worked those problems out. Each problem was slightly different. One was a more straightforward, simpler problem, and probably a problem that we would see more frequently. The second problem about satisfaction amongst the United States is a slightly different problem that we have to use different methods to generate our expected values. Okay, and so if you have any questions about either of these methods, I ask that make sure that you email me or that we will talk about it in class. But what we're going to do is we're going to be performing our own lab and we're going to be using our own data to generate our chi-square values. All right, so this is important that we have this skill now so that we can put it into practice later. All right, guys, take care, and I'll see you guys in class.